Unit 7, Energy and Reactions, Lecture 2. Now we're ready to talk about heats of reaction, in which we're going to apply a lot of the stuff that we've been talking about. In a chemical reaction, the delta H for the reaction is the sum of the delta H's of the products minus the sum of the delta H of the reactants. Folks, we said that just a little while ago. And remember that for a constant pressure reaction, the QP is equal to the delta H, or the delta H is equal to the QP. Either way you want to say that. That is for a constant pressure reaction. And we're not at this point dealing with constant volume reactions. Let's calculate the heat of this reaction. H2 gas plus Cl2 gas producing 2HCl. When you go to a table of thermodynamic data and you look up H2, what do you get? You better get 0, because at standard state conditions, the heat of formation of hydrogen gas when it's in the diatomic form is 0. That's its most stable form at standard state conditions. And the same thing is going to hold with chlorine. These are some of the diatomic elements. So those values are both 0. Now, we have 2 moles of HCl gas, and the delta H for HCl gas, or the enthalpy of formation, is minus 92.31 kilojoules per mole. Where did those values come from? Well, you can probably remember the ones about the elements at standard state conditions, but you're going to have to go look them up somewhere. So go look at a table of selected thermodynamic values. So we have the delta H of the reaction is equal to the sum of the delta H's of the products minus the sum of the delta H's of the reactants. Let's substitute in here. The delta H then for the reaction is equal to 2 moles times minus 92.31 kilojoules per mole. That is for the product, 2 moles of HCl, minus 0 kilojoules per mole, because both of the reactants were at their standard state conditions. They were elements at standard state. Working this out then, the delta H for the reaction is minus 184.62 kilojoules for 2 moles of HCl gas. Is the reaction endothermic or exothermic? Well, folks, look at it. Delta H is minus 184.2 kilojoules per mole. Delta H is equal to QP. If delta H is minus 184 point so-and-so, then QP is minus 184 point so-and-so. And when Q is negative, you know the reaction is exothermic. That's right. That's the amount of heat that is given off from the energy account. You might think of it being like this, that H2 gas plus Cl2 gas is going to produce 2HCl plus 184.62 kilojoules of energy that is given off. How much heat would be evolved if we were only concerned with 1 mole of HCl? Well, it's kind of obvious, isn't it? And you can certainly take that 184.62 kilojoules that is evolved and divide it by moles, number of moles, 2 moles, and you would have the heat per mole. Remember that, because you'll see some problems like that. Let's calculate the heat of combustion of 2 grams of acetylene. And we're going to do this by knowing the heats of formation of each of these substances. Now, I've given you the equation. 2 moles of acetylene plus 5 moles of oxygen, producing 4 moles carbon dioxide and 2 moles of water vapor. Now, the 2 moles of acetylene, I multiplied 2 moles of acetylene times 226.7 kilojoules per mole. That is what I got as the heat of formation of acetylene from its elements at standard state conditions. Yeah, I looked it up. What about the oxygen? That's 0. That's right. You're getting the idea? Now let's come over to the products. 4 moles of carbon dioxide times minus 393.5 kilojoules per mole. And what about for the water vapor, or water in the gaseous state? It's going to be 2 moles times minus 241.8 kilojoules per mole. All right. Now remember, the delta H for the reaction is equal to the sum of the delta H's of the products minus the sum of the delta H's of the reactants. So the delta H for the reaction is going to be 4 moles times minus 393.5 kilojoules per mole plus 2 moles times minus 241.8 kilojoules per mole. That is the sum of the delta H's of the products. Now from that we subtract the sum of the delta H's of the reactants, which is 2 moles times 226.7 kilojoules per mole plus 0 for oxygen. This gave me a heat of the reaction, or heat for combustion of the reaction, of minus 2,509.4 kilojoules, but that is for 2 moles of acetylene. I didn't want 2 moles of acetylene. I wanted the heat of combustion of 2 grams of acetylene. So I take my 2 grams, and when I add up the weights, I know that it's 1 mole per 26 grams, times, I know that 2,509.4 kilojoules of heat is evolved for 2 moles of acetylene. Let's see what cancels. Grams cancel, moles cancel, and I'm going to be left with minus 96.5 kilojoules. And that is the heat of combustion of 2 grams of acetylene. I hope you can look at this and see a lot of potential for solving certain kinds of problems. Hess's Law. Hess's Law tells us that the total energy change for a reaction is the same, regardless of whether the reaction occurs in one step or in several steps. This is also called the law of constant heat summation, or Hess's law of constant heat summation. Now, for example, we can produce carbon dioxide a number of ways. We can do it by one step, or we can do it by several steps. In any case, the energy will be the same. We can take carbon, burn it in oxygen, and produce carbon dioxide. And when we do, if you look it up, you will find the delta H is minus 393.5 kilojoules. We've got carbon and oxygen both in their standard state conditions and their most stable state. Now that's one way of doing it. Let's look at another way. We could take carbon and burn it with oxygen and produce carbon monoxide, for which the delta H is minus 110.5 kilojoules. Then we could take that carbon monoxide plus more oxygen and produce the carbon dioxide, a step for which the delta H is minus 283.0 kilojoules. Now, add it up. And you see that the delta H is minus 393.5 kilojoules, even though we did it in 2 steps. It's the same as if we had done it in 1. The heats are the same, but are the reactions the same? Well, let's look. If we take the carbon monoxide that is produced in the first reaction in part B, it will cancel the carbon monoxide that is absorbed in the second part of that reaction. Let's see, will anything else cancel? I don't think so. So let's add those two halves, if you will, of the total that we're going to make algebraically. And we get carbon plus oxygen gives us carbon dioxide. And the delta H is still negative 393.5 kilojoules. This has a lot of promise. Let me show you an example of the potential that this thing has. Suppose you need to find the molar heat of formation of manganese dioxide. So you go look it up in a variety of reference sources and you cannot find it. Well, is there another way you can do it? And the answer is yes. Find some equations that, when combined properly algebraically, will give you the equation for the molar heat of formation of manganese dioxide. Let me show you. First, write the equation you need. And here it is. Manganese plus oxygen gas giving you manganese dioxide solid. These, of course, are the most stable states. They're the elements in the most stable states at standard state conditions. Now, I've given you two equations up here, and I want you to combine them in such a way that you will generate that equation itself. Well, you need to start with the manganese. So let's combine them to achieve that. You need to start with the manganese. So that's the only place the manganese appears like that. So write it down. There it is. You've got the manganese now over on the left-hand side. You just have to get rid of a few other things now. Well, let's see. What's the heat involved with this? And the heat for that, the delta H, is minus 250.4 kilojoules. All right, now what? Well, we've got the manganese in the reactants, and of course oxygen will be easy enough to get in the reactants. Yeah, because that oxygen's in that second one, that second equation, and we also need to get the manganese dioxide on the right, so what we need to do is take this equation and flip it over. And when we flip it over and write it, we get this. Two manganous oxides plus oxygen produces the MnO2. And the delta H for that is minus 270 kilojoules. All right, let's take these things and add them algebraically. One MnO2 will cancel one of those two MnO2s. Do you see? And the two MnOs will cancel the two MnOs, and look what we are left with. We are left with manganese plus oxygen giving MnO2 solid. And the delta H is going to be minus 520.4 kilojoules. That's right. There are all kinds of things that you can do with this and the heats that you can calculate. In this problem, we are asked to use Hess's Law and to calculate the delta H for this reaction, in which fluorine molecules break down into fluorine atoms all in the gaseous state. And we're asked to do that by using appropriate manipulation of these three equations. All right, how shall we go about this? Well, I'm going to start with the F2, which is supposed to be on the left. And so I go shopping for it over here, and oh yes, there it is on the left. So I write that equation just like it stands. 1/2 H2 plus 1/2 F2 is going to produce HF in the gaseous state. But you will notice that up here I have two fluorines, so I'm going to have to double this. And so the delta H for this is minus 271 kilojoules, but I have doubled the reaction, so I must also double the heat consideration. All right, now let's see if we can get the fluorines in here. Do you see fluorine atoms anywhere? Sure, there they are right there. So let's write this equation, which is HF producing hydrogen atoms plus fluorine atoms. Yeah, that looks good. And the delta H for that is plus 568 kilojoules. Oh, but wait, is that going to work? We used a 2 here, which means we're going to have 2 HFs, so we're going to have 2 HFs here. That means we must double this, and we must also double the energy consideration. All right, let's cancel. What will cancel? Well, this will cancel this. Oh, that's good. I don't see anything else that will cancel. And how am I going to get rid of all this hydrogen stuff? I better bring in that third equation. That third equation is H2 gas producing 2 hydrogen atoms. Yeah, how's that going to be? Now that's not going to work. I've got the hydrogen on the same side here that I've got it here. We've got to get rid of that. So let's go back and erase some of this and turn this equation completely around. Yeah. So instead of writing it the way we wrote it, we need to write it as 2 hydrogens forming H2. Now, you remember that the delta H here was plus 436 for the way it's written. But we have to reverse it. So we've got to reverse the sign on that. So the delta H then is going to be equal to minus 436 kilojoules. All right, let's see how we're doing. Does everything cancel? These 2 hydrogens cancel these 2. This cancels this. Oh, look. All that we have left is what we are looking for in our equation. We have F2 producing 2F. Now, what do you come up with for the delta H? Add them up. Don't forget to change signs where necessary. Don't forget to double where necessary. And when I work this through, I come up with plus 158 kilojoules. What a neat problem. Heat capacity. There are some terms that we need to discuss with respect to heat capacity. One is heat capacity itself. And heat capacity is the energy required to raise the temperature of a body, the entire body, 1 degree Celsius, without changing its state of matter. The units are joules per degree Celsius or kilojoules per degree Celsius. Now remember, this is without regard for the size of the body. So of course, if you change the size of the body, you're going to change its heat capacity. Now, consider molar heat capacity. Molar heat capacity is the energy required to raise the temperature of 1 mole of a substance, 1 degree Celsius, without changing its state of matter. Molar heat capacity, that one's going to be easy to remember, isn't it? The units are joules per mole degree Celsius or kilojoules per mole degree Celsius. Just remember, this is specifically for 1 mole of a substance. Well, what about specific heat? You've heard of specific heat. Did you know that the full name is specific heat capacity? And it is the energy required to raise the temperature of 1 gram of a substance, 1 degree Celsius, without changing its state of matter. So think of specific heat as being heat capacity specifically for 1 gram. The units, joules per gram degree Celsius or kilojoules per gram degree Celsius. Remember, this is specifically for 1 gram of a substance. I want you to look at some specific heats. Look at water. Water has a specific heat of 4.184 joules per gram degree Celsius, as long as you're keeping water in the liquid state. We will talk about other specific heats for water in its other states of matter later, not right now. 4.184 joules per gram degree Celsius is something you are expected to know. Now, you look at that and say, okay, so I need to know that. Yes, you do. But you also need to know that is exceptionally high. That is a very high specific heat. Look, for example, at iron. Iron has a specific heat about 1/10 as much. Copper, even less. Lead, oh, it doesn't take much heat at all to raise the temperature of a gram of lead a degree Celsius. Gold, about the same as lead. And silver is quite a bit more than gold, but certainly considerably less than water. Let's do a quick exercise. I want you to multiply the specific heat of each of these metals by its atomic weight. Now the metals, just the metals. So take iron and look up its atomic weight, it's 55.85 grams per mole, and multiply that. And when you do, you come out with 25.1 joules per mole degree Celsius. Now what you have done is you have converted the specific heat to the molar heat capacity. Do you see that? You have brought it to joules per mole degree Celsius. Do the same thing with copper. So we take copper and multiply it by 63.54 grams per mole, and that gives us a specific heat, a molar heat capacity of 24.6 joules per mole degree Celsius. Look at lead. Multiply it by its atomic weight, 207.2 grams per mole. You get 26.5 joules per mole degree Celsius as its molar heat capacity. And gold, multiply it and you get 25.4 joules per mole degree Celsius. And silver, 25.6 joules per mole degree Celsius. What a surprise! What we're showing is that when you're talking about molar heat capacity, the molar heat capacity for most of your metals with atomic weights greater than the atomic weight of calcium are very nearly the same. We have a general formula that we use that says specific heat of a metal times its gram atomic weight will give us about 25.5 joules per mole degree Celsius as its molar heat capacity. So, the molar heat capacity of most metals whose atomic weight is greater than calcium's is about 25.5 joules per mole degree Celsius. That can be a handy piece of information to have tucked away somewhere. Determine the specific heat of iron. Well, you say, well, I just had it back there. I'm not going to let you go back. You've got to calculate it. So you say, okay, well, the specific heat of iron times its atomic weight, expressed as its gram atomic weight actually, is 25.5 joules per mole degree Celsius. Specific heat times 55.85 grams per mole is about 25.5 joules per mole degree Celsius. So the specific heat is about 0.457 joules per gram degree Celsius. How accurate is that? Well, the National Bureau of Standards lists the specific heat of iron as 0.452 joules per gram degree Celsius. Ladies and gentlemen, that is pretty good agreement. Estimate the heat needed to raise the temperature of 250 grams nickel by 130 degrees Celsius. In other words, we want to take it from something to something, and the range is 130 degrees. Well, the specific heat times the atomic weight is 25.5 joules per mole degree Celsius. You want to pause this and do it yourself? Do, and then come back on, and I will show you how I worked it. The specific heat times 58.7 grams per mole gives us about 25.5 joules per mole degree Celsius. So the specific heat then is going to be 25.5 joules per mole degree Celsius divided by 58.7 grams per mole. Cancel your moles, and when you do, you come out with a specific heat of 0.434 joules per gram degree Celsius. In other words, it takes 0.434 joules to heat a gram of nickel 1 degree Celsius without changing its state of matter. So we take our 0.434 joules per gram degree Celsius, multiply it by 250 grams, and multiply it by 130 degrees Celsius. Grams cancel, degrees Celsius cancel, and we find that it's going to take about 1.41 times 10 to the 4th joules to heat that nickel. It is handy to know. Calorimetry. What is calorimetry? Well, it's the study of heat changes by using a device called a calorimeter. Now, here's an example of a coffee cup calorimeter in which you take 2 styrofoam cups and nest them, or two cups made of a material that does not allow heat to pass through very well, and just nest them so that you have it like a thermos. But put a lid on top of it and put a thermometer through a hole that you've punched in the lid, and you've got a pretty good calorimeter. There are others that are fancier that look more like thermoses, but this one really works rather well. Now let's use that and recall our first law of thermodynamics. Do you remember that we said that the delta E for the system plus the delta E for the surroundings must be equal to 0? Or, if you will, look at it like this. The heat in plus the heat out must be equal to 0. Well, in the last problem when we were dealing with nickel, we showed that the heat in, or that heat of a particular body, was the mass times the specific heat times its change in temperature. Therefore, we can say that the mass times the specific heat times the change in temperature going in plus the mass times the specific heat times the change in temperature coming out has to be equal to 0. Not making sense? Let me show you. What is the final temperature if 20 grams of iron at 440 degrees Celsius is placed in 300 milliliters of water at 20 degrees Celsius? Well, the Q for the iron, that's the hot item, plus the Q for the water has got to equal 0. That means that the MC delta T for iron plus the MC delta T for water must equal 0. The iron is going to lose heat. Where is it going? It's going to the water. The water is going to absorb heat. Where did it come from? The iron. So when you add the two together, it has to be 0. You don't have any that is going to be lost elsewhere. So we take your 20 grams of iron with a specific heat of 0.450 joules per gram degree Celsius, you can always calculate it if it isn't given to you, times the change in temperature, and delta T is the final temperature minus the initial temperature. So it's T sub F minus 440 degrees Celsius, plus 300 milliliters times about 1 gram per milliliter, times 4.184 joules per gram degree Celsius. That's something you were born knowing. Well, times 4.184 joules per gram degree Celsius times the final temperature minus the initial temperature has got to equal 0. Doing your algebra, and you're good at algebra, you will find the final temperature is 23 degrees Celsius. Very easy, isn't it? The iron lost the heat, the water gained the heat. And we wanted to find the final temperature. Well, the iron is going to lose heat and the water is going to gain heat until they come to the same temperature. Remember, heat transfers from a hotter body to a colder body? That's right. So the final temperature is 23 degrees Celsius. Looks simple enough, but there's a problem. You see, if this were to occur in a calorimeter, we must consider the heat absorbed by the calorimeter also. So the first thing that we have to do before we can really work a problem like this is determine the heat capacity of the calorimeter. Here's how you go about determining the heat capacity of a calorimeter. There are other ways, but this is a pretty quick way of doing it. Add a measured quantity of water to a clean, dry calorimeter. In other words, pour some water that you know how much you're pouring into a nested coffee cup calorimeter that you've cleaned and dried. Allow it to sit for a few minutes and come to equilibrium so that the calorimeter and the water are the same temperature. Read and record that temperature. Now, add a measured quantity of hot water whose temperature is known to the contents of that calorimeter. Stir and determine the final temperature. Don't let it sit too long. It'll start cooling off to the air unless you really have it sealed well. Here, let's work one. When 20 milliliters of water is added to a calorimeter, the temperature is 20 degrees Celsius. A 30 milliliter sample of water at 90 degrees Celsius is added, and the final temperature comes to be 56 degrees Celsius. We need to find the heat capacity of the calorimeter. Well, you say that hot water is going to lose heat to the cold water. Yeah, it's going to lose heat to the cold water, but it's also going to lose heat to the calorimeter. So we have to account for that too. So we use this expression. The Q for the hot water plus the Q for the cold water plus the Q for the calorimeter must equal 0. So let's start with the hot water. We take our 30 ml sample, which if we use our 1 gram per ml means it weighs 30 grams, times the specific heat of water, times, now remember, change in temperature is final minus initial. The final temperature is 56, the initial was 90. Okay, so that is the Q for the hot water. Now let's go to the Q for the cold water. Well, the cold water is going to be 20 grams times 4.184 joules per gram degrees Celsius times 56 minus 20 degrees Celsius. So that is the heat then that is absorbed by the cold water. And then, of course, you have the Q for the calorimeter, and that is equal to 0. Now stop this for a minute and work it out. When I worked it out, I came up with the Q for the calorimeter being 1,265 joules. But that is the heat that the calorimeter gained. I need the heat capacity. Heat capacity takes into consideration the range of temperature over which this was absorbed. So I take this heat, and it is absorbed over a range of 36 degrees Celsius as it goes from 20 degrees Celsius to 56 degrees Celsius. So it's 1,265 joules over 36 degrees Celsius gives me the heat capacity of the calorimeter at 35 joules per degree Celsius. And as long as I'm using that calorimeter, and as long as it's clean and dry, I would know that its heat capacity is going to be 35 joules per degree Celsius. Got it? Good. Now let's use that. When 2.4 grams sodium hydroxide pellets, or solid, is added to 100 milliliters of water in that same calorimeter at 21.2 degrees Celsius, the temperature rose to 24.3 degrees Celsius. We need to calculate the molar heat of dissolving sodium hydroxide, and I'm giving you the specific heat of the sodium hydroxide solution that's produced. So what we're doing is we're starting out with 2.4 grams of sodium hydroxide and dropping it in 100 grams of water. And the water and the calorimeter are at 21.2 degrees Celsius. And when we add the sodium hydroxide to it, the temperature goes up. Okay, so that's a reaction that's occurring, if you will. So what is the equation that we're going to write? Well, I see it like this. The Q for the reaction, so we have the heat that is involved in being given off by the reaction, is being picked up by the solution and the calorimeter. So we have the Q for the reaction plus the Q for the solution plus the Q for the calorimeter must be equal to 0. Okay. the Q for the calorimeter, the Q for the reaction plus 102.4 grams. Now, where did that come from? That came from the 2.4 grams of sodium hydroxide solid and the 100 milliliters of water at 1 gram per milliliter. So that's where we get the 102.4 grams, the mass of that solution, times its specific heat, times 3, plus 35 joules per degree Celsius times 3.1 degrees Celsius. Where did that come from? That was the heat capacity of the calorimeter that we calculated earlier. And the temperature change for the calorimeter is the same as the temperature change that is being undergone by the rest of that in the container. Well, when we work it out, the Q for the reaction is that it evolves 1,445 joules for 2.4 grams of sodium hydroxide. But the problem asks for the molar heat of dissolving. So I'm going to take that 2.4 grams of sodium hydroxide, and I know that a mole of sodium hydroxide weighs 40 grams, so that tells me I'm dealing with 6/100ths of a mole. And that is producing 1,445 joules of heat when that 6/100ths of a mole dissolves in that solution. Tells us then that we have a heat evolution of 24,000 joules per mole, and that is the molar heat of dissolving sodium hydroxide. Yeah. Well, we've covered a lot of material. We talked about the first law of thermodynamics, which you now know is the law of conservation of energy. We talked about enthalpy and what it means, and we talked about standard state conditions and things of that type. We talked about heats of reaction and brought in Hess's Law. We talked about heat capacity and the several kinds, and then we went through a section on calorimetry. A better way to teach and learn chemistry.